Hello, I'd like to show you how to use the Agios Energy Lab tool to estimate and measure power for an NXP IMX8 Quad-X Plus. I will then also show you how we optimize power consumption using the Agios Seed software. If we take a look at the monitor here, we can see the Energy Lab tool in action. Energy Lab is an integrated development environment for creating and analyzing power models of your system based on the IEEE P2415 UHA standard. Energy Lab is also used for configuring and generating the seed firmware for your target. On the left, we see a choice of different views of the model. By default, it's a view of the system hierarchy. I have already loaded a model of the IMX8 system, so this is what we see here in the central area. We've got the NXP MEK board at the top level, containing the IMX8 Quad-X Plus SoC, as well as other board components such as the PMIC and the DDR chip. If we take a closer look at the IMX8 SoC, we can see its different subsystems, including processors, buses, memories, and peripherals. The IEEE P2415 UHA model contains all the power-related details relevant from a software and system developer's point of view. In addition to power states and power models, it also covers transitions and latencies, and most importantly the dependencies. Dependencies between different components, as well as dependencies on the clock or voltage trees. Incorporating dependencies ensures that during simulation only states are entered that are feasible in a real system as well. The UHA model can easily be extended to cover your particular configuration, from application-specific peripherals to a complete custom board or system. But aside from modeling the hardware, Energy Lab also lets you model your software as UHA tasks. A task expresses the software's dependencies on the hardware, as well as on other software such as operating systems or middleware. The use case we are looking at here is stolen vehicle tracking, a common telematics application. We've created a task we call GPS transmit, which depends on the telematics active state, but also on the GPS module to be on. Energy Lab lets us follow the dependencies via hyperlinks, so we can jump to the telematics task and from there to the Linux OS task, which includes various hardware dependencies reflecting the Linux configuration we're using. Now that we've modeled our system, we are ready to start the simulator. This brings up the Energy Lab simulation window. This window is organized like a debugger. On the left, we see the scenario file, which is essentially a sequence of timestamps and events. Using the control buttons in the toolbar, I can run through my use case or single step through it. Our plot area now shows the computed energy profile for our use case. Energy Lab now lets me see more details such as the top consumers in my system, or the transition latencies, or details about the state of a particular component. Energy Lab has many other features that make it easy to further optimize power for your system. But now I'd like to show you how we can apply such optimizations to the actual target device by configuring and generating a customized seed power management firmware. The seed configuration dialog allows me to choose from various optimizations, either globally or individually, where I can enable features such as frequency scaling of the AXI bus or DDR controller, letting devices enter optimized idle states when unused, or by scaling the voltage of the main supply rails. It essentially allows me to enable complex power optimization features from a user-friendly UI. Additionally, Seed offers helpful diagnostic features that help troubleshoot power-related problems. Let's now take a look at the NXP IMX8 Quad-X Plus MEK board. To measure power on this board, we used shunt resistors on each of the voltage rails. Energy Lab can interface with data acquisition devices to get accurate power measurements in real time for multiple voltage rails. To start the application, I'll insert the SD card, including the Seed software, and then turn the board back on. Now we can click on Energy Lab's Test and Measure button up here, select the appropriate board type, and connect to the LabJack DAC device, which we've got hooked up to the shunt resistors on the IMX8X board. The power consumption is plotted in the main area here, And we have the terminal window at the bottom where you can see the prints from Linux and the Seed embedded software. Once Linux completes its boot procedure, we can start Seed and the stolen vehicle tracking application. In this use case, the system will periodically acquire the GPS location and transmit it. Therefore, Seed keeps the system in its lowest sleep state most of the time and only wakes up the application processors once a minute to perform their activity. The power plot shows the power of the SoC broken down by voltage rail. On the right, you can see a numeric summary in table form, which can also show total energy or projected battery life. Currently, we can see that the power consumption is around 70 milliwatts, with most of it coming from the 3.3 volt rail that also powers some onboard peripherals, which aren't completely off while the IMX8 is in its low power state. As soon as Linux resumes, the GPS transmit task is executed. This way, Seed keeps the Cortex-A35 application processors on for only a few seconds at a time, minimizing the energy profile of the use case. This allows for the stolen vehicle tracking application to be powered from a small backup battery for the required amount of time. Additionally, Seed allows for the same power optimizations to be applied when the Zen hypervisor is included in the telematics software stack. This makes it possible to achieve the same energy profile when Linux is running as a guest on top of Zen on an IMX8X processor. I hope you've enjoyed this video. If you'd like to learn more about Energy Lab or Seed, please consult our website at agios.com. Thank you for watching.